Hi ladies and gentlemen, today we are going to show you how mass transfer is involved in a very simple everyday process, making tea. We will be preparing tea with water at 3 different temperatures with the same amount of tea leaves. After letting them soak for a minute, we will analyze these samples in a UV-vis spectrophotometer to determine the difference in concentration of the solution and correlate this with diffusion rates.
As a start, this is a bag of turmeric ginger tea brought from RTH Cafe. First, cut the tea bag open to weigh out sample of roughly 0.1 to 0.12 grams. We are first going to place this weighing paper on scale and zero the scale. Then we will carefully place tea leaves onto the weighing paper until it reaches a mass somewhere between 0.1 and 0.12 grams. This first sample is 0.1030 grams. Repeat for a second sample. Ours ends up being 0.1127 grams, and the third sample which ends up being 0.1150 grams.
Now that we have measured out the amount of tea, we will pour the samples into their corresponding Erlenmeyer flask while putting a beaker of distilled water on a hot plate to heat up. Once the water reaches a boil, pour out 15 ml into a graduate cylinder. This will be the hottest of the 3 control temperatures. Similarly, pour out 6 to 8 ml of the boiling water into a graduate cylinder, and then add some room temperature distilled water until the total volume is 15 ml. This is the medium temperature. Lastly, pour out 50 ml of room temperature distilled water into a graduate cylinder. This is our lowest temperature. Now, measure the exact temperature of each water sample with the thermocouple and record the temperatures. As you can see here, our temperatures are 20.1 degrees, 45.9 degrees, and 66.9 degrees.
The next step is to pour these water samples into 3 different tea samples in their respective flasks simultaneously. Once all the water has been poured, start a timer and wait until 1 minute has passed. After the time is up, simultaneously pipette each sample into their own cuvettes and analyze them in a UV-vis spectrophotometer one after another to obtain their different absorbance spectra. According to Beer-Lampert law, there is a direct correlation between absorbance and concentration. Calculating the concentration will give a relative comparison of diffusion rates with respect to time, in this case 60 seconds, by Fick's law of diffusion.
From the Wilkie chain equation, diffusivity is calculated as follows, where phi of water is 2.6, molecular weight of water is 18.016 grams per mole, and the molar volume of curcumin, which is the main dye component in turmeric tea, at its normal boiling point is calculated to be 415.6 centimeters cubed per mole, from table 2.2.3 in the Bergstore Lightfoot textbook. As you can see, all the carbon and hydrogen volume in the molecule are added in addition to 2 oxygen atoms, 2 OH bonds, and 2 ether bonds. 2 benzene ring volumes are subtracted as the ring occupies less space than 6 carbon atoms in linear or other arrangements. From the water viscosity table, we have found the viscosity of water at 3 different temperatures in which we ran our experiment in. The viscosity of water at 20.1 degrees Celsius is 1.0016 centipoise. The viscosity of water is 0.5958 centipoise at 45.9 degrees Celsius and 0.4329 centipoise at 66.1 Celsius. These values will then be plugged into the Wilkie chain equation in the next slide. Here is the sample calculation for calculating diffusivity using the Wilkie chain equation for the first temperature of 20.1 degrees Celsius. Note that the temperature is in Kelvin, calculated by adding 273 to the temperature in degrees Celsius, which in the first temperature's case is 293.1 Kelvin. The viscosity used is in centipoise, which at 20.1 degrees Celsius is 1.0016 centipoise. The result, by plugging in everything into the Wilkie chain equation, is 3.98 times 10 to the negative 6 centimeters squared per second for a temperature of 20.1 degrees Celsius. A similar calculation was done for the remaining two temperatures, 45.9 degrees Celsius and 66.1 degrees Celsius. The viscosity used for each temperature corresponds to the temperature listed in the earlier slide, talking about viscosity of water at different temperatures. The calculated diffusivity for temperatures of 45.9 and 66.1 degrees Celsius are 7.28 times 10 to the e to the negative 6 centimeters squared per second and 1.07 times 10 to the negative 5th centimeters squared per second, respectively. Now that we have obtained the diffusion constants, let's take a look at how to find the concentration of curcumin in water at those three different temperatures. Recall that we used UV-Vis spectrophotometer to measure the absorbance of each temperature sample. From experimental data, we're able to use the Beer-Lambert law, A equals epsilon B C, to find concentration. In this equation, A stands for absorbance, epsilon is the molar absorptivity of the solute in solvent, B is the path length, and C is the concentration of the solute. We have set the path length to the standard 1 cm since our cuvette used was standard. From reference, the molar absorptivity of curcumin in water is approximately 19,900 to 66,060 per molar per centimeter. We have picked a rough midpoint of 30,000 per molar per centimeter for our estimation. The absorbance measured from experiment at 20.1 degrees Celsius, 45.9 degrees Celsius, and 66.1 degrees Celsius are 0.167, 0.421, and 0.994 correspondingly. Plugging all the values into Beer-Lambert law, and we get 6 to the 10 to the 6th molar, 1.4 10 to the 5th negative 5th molar per liter, and 3.3 times 10 to the negative 3rd molar correspondingly. All results are summarized in this table shown here. As we can see, as temperature increased, the diffusion constants increased since there are more Gibbs free energy for the curcumin molecules to diffuse out of the tea leaves and into water at a faster rate, causing concentration of curcumin in water to increase as more curcumin is able to diffuse out of the tea leaf and into water within a set amount of time, since the diffusion rate became faster. From this experiment, we can see that even simple daily activities such as making tea revolves around fundamental science principles such as mass transfer, diffusion, and temperature. Science is everywhere. Now, where is your science?